Hello, my name is Raymond Sullivan, and I am here to talk about the incredible fun of energy, momentum, and electromagnetic waves. I picked this topic in particular because I felt I could talk about electromagnetic waves and energy for hours, quite honestly, but I decided to keep it to 5 to 7 minutes because of certain limitations imposed. And so here it goes. Energy, first of all, is important to us because it is the ability of a physical system to do work, and it can be measured in joules. An important property about energy that we have found out is known as the law of conservation of energy, which allows us to derive energy in many forms, such as Newton's, Pascal's, where Newton's is the force of a mass, or the acceleration of a mass that can be calculated and gives us force. Pascal's is basically the force per unit area, and in particular, I want to talk about watts, which is joules per second, or the energy rate conversion of a system, which will be applied into one of the problems that I'll be talking about today. Another important part that I'm going to talk about is electromagnetic waves. As we've done many of these problems, we always have to consider the direction and the strength of electromagnetic waves. Electromagnetic waves depend upon, electric charges. They create magnetic fields, and thus we have a property that allows us to determine and use very practically in many aspects of real life. See, our electromagnetic waves depend on the power and their frequency, which I'll talk about more a little bit later. And because the power and frequency that electromagnetic waves have, we are able to use them in many, many different ways that are applicable to our lives. And I'm sure that despite all that we know about electromagnetic waves and energy, we will still be learning a lot more in the future. So, the book problem that I chose was 32.16 because it had a bio application star next to it, and I am a science major, so I'm always interested in seeing little things like this. So the energy, so the problem reads that scientists are working on a new technique to kill cancer cells, which is actually not true. This is a normal technique nowadays, but I guess this book's a little dated. So they use about 2 times 10 to the 12 watts of energy in short pulses of light, a few nanoseconds, which makes sense because the short pulse allows for a high frequency, so you can bombard this cell really quickly. And the goal is to basically, attack the interior of a cell without causing it to explode, but just um, allow it to die there. And so you will only affect that particular very, very, very small region. And this pulse that's so I calculated, the first question it asks is to how much energy is given to the cell during the pulse. And so using these two, you find that it's 8 times 10 to the third. Also, part of the problem says that this pulse is given over 100 cells, so it's about 80 joules in this single pulse that kills brain cells, or mainly it's used for attacking brain cells for tumors that are very specific, and nowadays it's actually even targeted towards tumors in general. So 80 joules of energy are used. And in more relative terms, it asks us, to find out the intensity delivered. And so, you use the energy used in the pulse, and then the area of our cell. So 100, pi r squared, or this is the radius of the cell. And so we get 1 times 10 to the 21 watts per meter squared. And just to put that in terms of, comparison, relative terms, 75 watts, a 75 watt light bulb has about 330 watts per meter squared, and this is shown in problem 32.17. It's one of the homework problems that we did once. So 330 watts in a light bulb. We use 10 to the 21 watts per meter squared in this laser pulse. This is why it can kill cells instantly. That's why it's such an efficient method. And then later it even asks us to, calculate the magnetic field of this. So to calculate the magnetic field, we know our intensity, we know our regular E naught and speed of light term, and we can find our electric field, which is volts per meter. And then we find our magnetic field, which would be 2.9 times 10 to the third Tesla. That's 2,900 Tesla. That's a pretty hefty magnetic field, but it makes sense in terms of the calculations because guess what? This is how they're able to, attack this instantly the cell so quickly, and that's why it's a laser, because it causes damage right away. Obviously, this wouldn't be able to be done like a large scale laser. You wouldn't be able to have 20,000 Tesla lightning laser. That would be unrealistic. But because it's such a short pulse and then it's a small concentrated laser, you can do this and attack cells. And that's why mainly I wanted to talk about electromagnetic waves and energy, because I think it's interesting that we can do these things with lasers in medicine. And secondly, this is a second live application, but it's just nothing that it's on the book and something I had to research by myself. And I want to talk about GPS and how waves work on GPS. So GPS, I learned that work in a system of 24 satellites where 4 know your position at all times. They send out radio signals, which work in forms of trilateration, where 3 satellites give you longitude and latitude, and then the fourth one will give you the elevation of your position. But now the important part in terms of waves and direction is how they operate at frequencies. You see, they operate at 2 very specific frequencies, 1575 and 1227.6 megahertz, and these are megahertz frequencies because these particular numbers, God knows why, actually. I mean, I'm sure physicists know why, but they eliminate ionospheric effects. And the ionosphere effects, the ionosphere is basically the sphere where we have a lot of ions and concentrated electrons, and they can interfere with the magnetic waves. But at this intensity or this frequency, where it's a much larger wavelength, then it can overcome the ions in the atmosphere, in the sense that we can still receive the signal on Earth. So it's got to be it's a pretty large frequency that the satellite has to send out, but it's the marvel of having a GPS system, and that's what I wanted to talk about. So that's my video. Have a good Christmas, and it's been a pleasure being in your class, Dr. Cormier.